Welcome back. This is another exciting episode of Mr. Takeda Teaches Algebra. I'm your host, Mr. Takeda, and I'm going to teach you some algebra right now. This is lesson 2.6 on solving absolute value inequalities. Yes, those darn absolute values are back here. We thought we left them behind in the previous chapter of the equations, but here they are returning to us like a bad penny, and they're going to affect our inequalities. So we asked the question, how do you solve an absolute value inequality? Well, let's take a look. Okay, all this is saying here is to solve, this is the less than case, this is the greater than case, right? Less than, greater than. So to solve it, of course, C has to be greater than 0, C has to be positive, solve the compound inequality. Okay, so this is kind of like, this is actually the positive case. This one stays, the sign stays the same. Where the sign is reversed, we reverse the inequality symbol. And I'll go over that when we do some examples. We reverse inequality symbols because if remember when we multiplied and divided by a negative number, the sign changes, so we reverse the inequality symbol. Same thing's happening here. We're for the negative case, we reverse the inequality symbol. Same thing down here. But this is our OR case. This is the positive case over here on the right. This is the negative case, and they reverse that inequality symbol around again. So this is the OR case. This is the AND case. One way you might want to remember it is if we point to the left, point kind of to the smaller number, that's conjunction, and that's that's in alphabetical order. That precedes disjunction, which is pointing to the right. And another way you could maybe remember it is that in alphabetical order, conjunction is AND, which comes before OR. So everything's kind of in alphabetical order, but it all kind of comes off of this sign here, this sign right here, here, and here, that if it's to the left, if it's the smaller values, conjunction, if it's the larger value, disjunction. Okay, and then of course, that also applies to the and equal to things down here. Okay, let's go ahead and take a look at an example here. The absolute value of x plus 7 is less than or equal to 2. So that's going to give me, x plus 7 is less than or equal to 2. That's my positive case. My sign stays the same. But when I use my negative case, I reverse my inequality symbol around. So negative 2, reverse that inequality symbol around. Let's go ahead and solve this. So if I subtract 7 from both sides here, x will be less than or equal to negative 5. Over here, subtracting 7 from both sides, x is greater than or equal to negative 9. Okay, so writing this as a single statement conjunction, my smaller number goes to the left, negative 9. X is in the middle. My larger number, negative 5, is to the right, just like on the number line, and I'm pointing to the smaller number, so I'm always pointing to the left. I'm always pointing at smaller numbers. Okay, so let's go ahead and graph these here. Negative 9, negative 7, no, negative 9, negative 8, negative 7, negative 5, 4, negative 3, negative 1, and 0. Okay, so solid dots on negative 9 and negative 5. And then I want the numbers between them because this is conjunction. In other words, the solution has to be meet both these requirements, so it's between them. Let's take a look at B. The absolute value of 8x minus 11 is less than 0. Well, in this case, what do we know about absolute values? They're always positive. I'm going to ask you this, maybe a few more times this year. They're always positive. This says that this absolute value is less than 0. Anything less than 0 we know means negative. If something is less than 0, that means it's negative. So this one we can just tell right off the bat, this one is no solution. Okay, let's go ahead and try these examples in which the inequality points the other direction. So these are disjunctions. These are going to be OR. See, these are greater than symbols. Okay, so C, Minus 1 is greater than or equal to 5. And then C minus 1 will be less than or equal to negative 5. So if I add 1 to both sides here, C will be greater than or equal to 6. If I add 1 to both sides here, C will be less than or equal to negative 4. And this is an OR condition. B, I'm going to save room by not graphing. Hopefully you remember how to graph how to graph compound inequalities. Absolute value of 10 minus m is greater than or equal to negative 2. Well, let's just take a look and see what this means here. The absolute value of any of anything is positive. Remember, absolute values, what do you know? They're always positive. This says it's greater than negative 2. Well, all positive numbers are greater than negative 2. So it doesn't matter what I put in here, because once I simplify the middle and then turn it positive, it's always going to be greater than negative 2. So this one is going to be all real numbers. What's my solution? All real numbers is my solution here. Yes, and on the number line, it'll actually take the whole thing up. C. Now, C looks like it has a couple things going for it here. First thing I want to do is isolate the absolute value statement. So I'm trying to isolate this part here. I'm going to subtract 1 from both sides first. So 4 times the absolute value of 2x minus 5 is greater than 20. Dividing both sides by 4. And then dividing both sides by 4 will leave me the absolute value of 2x minus 5 is greater than 5. Okay, so once again, isolate your absolute value brackets first. Now we can write our two cases. Sound familiar? Does it sound like chapter 1? I hope so. Okay, so 2x minus 5 is greater than 5, and 2x minus 5 is less than negative 5. Okay, that's my negative case. So solving this here, if I add 5 to both sides, 2x is greater than 10, so x is greater than 5. Over here, if I add 5 to both sides, 2x, negative 5 plus 5 is like 0. So dividing both sides by 2, x is less than 0. I'm going to go ahead and graph this one, just because I went through all that trouble to solve this one. So boom, there's my graph. Okay, so my boundaries are 5 and 0. Oh, before I forget, I have to put an or in between these, right? This was a disjunction. Put a 0 here. 1, 2, 3, 4, 5. Open circle at 5, and I want the numbers greater than 5, so I'm graphing to the right. My other boundary is 0, so an open circle at 0, and I want the numbers going to the left of 0. There we go. And that's just, those are my disjunction examples. You are buying a new computer. Let's take a look at the word problem, since this video is only 9 minutes long so far. You are buying a new computer. The table shows the prices. Let me get the table in here. Oh, sorry, there's the table. The table shows the price of the computers in a store advertisement. You are willing to pay the mean price with an absolute deviation of at most $100. How many of the computer prices meet your condition? So this is similar to what we did on the equations. Let me give you a definition here for absolute deviation before we continue. Okay, the absolute deviation of a number x from a given value is the absolute value of the difference of x and the given value. This is like we did in the previous chapter with tolerances and minimum and maximums and nominals. That's basically what it's the same thing here. Okay, so first thing it says you're willing to pay the mean price with an absolute deviation of at most $100. So what this is saying is we want to select computers here that are within $100 of the average. So without watching all these calculations, I'm going to tell you that the mean price here equals $664. You added up all these computers here, all these prices, and divided by 10, you get 664. So my absolute value inequality then, look at the absolute deviation thing here, is the price of the computer minus 664. And that has to be what? That deviation has to be less than or equal to $100. It can be $100 more than 664 or $100 less than 664. Because remember, if I have a number in here, if it's smaller than 664, and I subtract 664 from it, it's going to come out negative. But then the absolute value makes it positive. Okay, so my compound inequality looks like this. Negative 100 has to be less than or equal to x minus 664, and x minus 664 has to be less than or equal to 100. So we'll find that we have 564 has to be less than or equal to x, and that has to be less than or equal to 764. So we're looking at computer prices that are between 564 and 764 inclusive. I mean, in other words, I can count 564 and 764. And that would be no, yes, yes, no, yes, yes, no, yes, and yes. A25 must be an apple. Okay, so we can buy those 6 computers. They meet our requirements. And let's see. Oh, concept summary. Let's get these in our notes. This is really it here. We're going to follow one step in multi-step inequalities. We follow the same step as equations. Like I said, they're cousins. Reverse the inequality symbol when multiplying or dividing by a negative number. That is a number 1 lesson from this chapter. Compound inequalities, if necessary, write the inequality as 2 separate inequalities. Solve them separate and include and or in the solution. Actually, I don't use the and. I write them, I'll write them like negative 2 is less than or equal to x, which is less than or equal to 5. I write it as a compound inequality. And then absolute value inequalities, if necessary, and we say this all the time, isolate the absolute value expression on one side of the inequality. Isolate it first, then write it as a compound inequality. Those are the basic one, 2, 3 things that we learned in this chapter. So only 3 real new things in this chapter, and that's it. The chapter test is coming soon. That completes our videos for chapter 2. I'll see you in class. Thanks a lot, and have a great rest of your day.